The next family we're going to look at is the absolute value family. The equation for absolute value functions would be y equals the absolute value of x, or f of x equals the absolute value of x. To graph the absolute value function, we're going to start at the vertex, which is 0, 0. And when we're at the vertex 0, 0, if we move right 1, we are going to be moving right 1 and then take the absolute value of 1, so up 1. So right 1, up 1. And then right 2, the absolute value of 2 is 2, so right 2, up 2. Then if I move right 3, I'm going to move up by the absolute value of 3, which is 3. Let's see what happens when I move left. If I move left 1, that's like putting negative 1 in for x. Well, the absolute value of negative 1 is positive 1, so if I move left 1, I'm still going to move up 1. Similarly, if I move left 2, that would be the absolute value of negative 2, which is also positive 2, so left 2, up 2. And you guessed it, if I move left 3, I will be moving up 3 as well. Left 3, up 3. Now this function continues in that pattern, so I'm going to end up with a nice straight line on this side and a nice straight line on this side. And for that reason, I have nicknamed the absolute value function the letter V. The domain of this function, as I scan left to right, it covers everywhere from negative infinity to infinity, so that is our domain. Negative infinity to infinity. The range is the y value, so I go from bottom to top. I start at 0 and continue going to infinity, so the range will be 0 to infinity. You can see that if you fold this graph over along the y-axis, it would fall exactly on top of itself. So it has y-axis symmetry, which means it is an even function. Now, where is this graph increasing and decreasing? As I move from left to right, if I start at negative infinity, the graph is going downhill all the way till x is 0, and then the graph starts going uphill from 0 to infinity. So it is increasing from 0 to infinity, but it is decreasing from negative infinity to 0. Where's the graph positive? In other words, above the x-axis. Well, it's positive everywhere except for right there at 0. So it's positive from negative infinity to 0, and then we skip over 0 because 0 is not positive or negative. So then it's positive again from 0 to infinity. And the graph is negative nowhere. Our last function family is going to be the reciprocal or rational function, and it is y equals 1 over x. Now this one is by far the strangest one that we will have encountered so far. To graph this function, you have to realize that you cannot divide by 0. So you can't have x equals 0. So for that reason, we start this one with a black hole at 0, 0, and force field lines. Now it's a little bit Star Trek at this point, but we start with a black hole at 0, 0 and force field lines. So I'm going to put an open circle for my black hole, which is actually a red hole, and then force field lines coming out of it, straight up and down, and going side to side horizontally. So that creates my force field. So my graph is not allowed ever to cross the vertical lines. Sometimes they'll cross the horizontal lines, but we'll see that a little bit later. And then from that black hole, we will move in this pattern. We will move right 1, and up, if I put 1 in for x, I'll get 1. So right 1, up 1. Then if I move right 2, put 2 in for x, I'll be moving up 1/2. So up 1/2. Right 2, up 1/2. Then I hate to put fractions out there, but that's what has to happen next. If I move right 1/2, 1/2, it's a reciprocal function. So when I take the reciprocal of 1/2, 1 over 1/2, I get up 2. So my other point is right 1/2, up 2. Now the rest of this graph, if I would put 4 in, I'd get out 1/4. If I would put 10 in, I'd get out 1/10. If I would put 1/10 in, I'd get out 10. So the rest of this graph just kind of rides really close to those asymptotes, is what they're called, and looks like that. Now we can also move left. So we can also move left 1. If I put -1, I'll get out -1. So left 1, down 1. If I go left 2, I'll be moving down 1 over -2, which is -1/2. So left 2, down 1/2. And if I move left 1/2, I'll be moving, you guessed it, down 2. Left 1/2, down 2. And then I'm going to connect those in the same way. And maybe you guys can come up with a better nickname than I have. I just call this one the swoopty swoopty because it's got 2 swoopty parts, so I know it's not very creative, but it's what I got. Oops, I forgot function notation. Maybe you already filled that out. F of x equals 1 over x. The domain of this graph. Now the domain of this graph is that it covers everything from -infinity all the way to infinity except right here at x equals 0. So the domain goes -infinity to 0 and then skips over 0 and goes 0 to infinity. The range does the same thing. Starts at -infinity and comes up, skips over that 0, and then goes 0 to infinity. What about symmetry? If I fold it over the y-axis, it doesn't land on itself, but if I rotate it 180 degrees, it does. So it has origin symmetry, which means that this is an odd function. Okay, where is this graph increasing? If I go from left to right across my graph, the graph is slowly going downhill until it gets here, then it's really, really going downhill. And then I got to skip over 0. Then if I start back up here again, my graph is really, really going downhill fast, and then it slowly starts going downhill. So this graph never goes uphill. So it is increasing nowhere. Now with the decreasing, it's decreasing from -infinity up to 0. But at 0, it's not decreasing. So we skip over and we start up again. Skipping over 0, it decreases all the way back out to infinity. Where is this graph above the x-axis? Cover up below, and we get it's above the x-axis from 0 to infinity. And below the x-axis, it will be below the x-axis from -infinity to 0. That is the last parent function that we have.